Now we start the second part of single sideband generation and modulation. In the first part, we have covered introduction, definition, time domain representation, and we have used Hilbert transform. We came up with the general form for the single sideband. In this presentation, we look at generation using two types, selective filtering and phase shifting. And then we'll look at demodulation of single sideband using coherent or non-coherent detection if we add the carrier. So, generation of single sideband. The general form for single sideband is m of t times cosine minus or plus mh, the Hilbert transform, times sine. We have derived this in the last video. Now, you use minus sign if you want the upper sideband or positive sign if you want the lower sideband. We can generate this expression by implementing the equation or by using selective filtering. In selective filtering method, we need to realize the filter based on spectrum, as we're going to see. And in the case of phase shifting method, we will try to implement this time domain expression. So we have two methods for the generation of single sideband. In selective filtering, we start with double sideband signal, and then using the multiplication by cosine, we get the double sideband. So from here to here is just direct multiplication by cosine. And now to get the upper side or the lower sideband, we use a band pass filter. If you want the upper sideband, you start at omega c or fc, and then you end up at fc plus b. That's the bandwidth of your filter. Unfortunately, this requires your filter to be very sharp, so you get exactly what you want to get the upper sideband. Similarly, we use the other type of filter. The only difference will be the bandwidth is going to be b, but now we go from this is fc, so this is going to be fc minus b up to fc. Now, if you do this, you get what we call selective filtering. What makes this possible is that in real life, the signal spectrum does not look like this, especially in voice applications. In fact, we have what we call a guard band. So from here to here, we have about 300 Hz. That's to say, the voice level, the frequency of our voice will start having residual amplitude above 300 Hz. So we almost have nothing below 300 Hz. Now, if you use double side, after you multiply by cosine, the guard band becomes 600 because you have 300 in the positive. Multiplying by double side by cosine make it double, which is 600. So this guard band makes selective filtering possible. Without the guard band, it will be impossible to design a sharp filter which is ideal. So this is the first method. In the second method, we basically implement the equation. So the equation says, take the message multiplied by cosine. We're taking the message. In the upper branch, we're doing the first expression, multiplying by cosine. And then in the lower branch, so this is the upper branch, will correspond to this. And the lower branch, we take, to correspond to this expression, we take the message and delay it by an ideal minus pi over 2 phase shift, which is nothing but Hilbert transformer. Then the message here become m sub h. Now we are not going to multiply m sub h not by the message, we need another phase shifter here, minus pi over 2, to convert the cosine into sine. They get multiplied, and then at the output, if you want the upper sideband, you use a minus sign. So this is a summer, it will sum, here plus always, and we can pick from the lower branch plus or minus, whether we want upper sideband or we want the lower sideband. Now you have to be careful that this phase shifter might be much easier to design because it's changing one frequency. But designing this phase shifter, it's much more difficult because it shifts all frequencies by minus pi over 2. So this operates at different frequencies. And designing the Hilbert transformer is not something easy. Now, in the following slide, we explain how the phase shifting method works. I want to get an idea about, in the spectrum, what happens. So this is kind of simplified version of this diagram. We start with the message spectrum here, and then once we multiply by cosine, the spectrum, this is the spectrum at this stage, so it's double sideband. So subtracting or adding this lower sideband is going to make the double sideband into single sideband. So let's see how this thing works. So in fact, what happens here, once you have a phase shifter by 90 degree, okay, as if you have taken the message, and because the phase shifter is odd, as if you're taking this part, the red part of the signal, and you make it into 90 degree here, minus 90, and plus 90 degree here. So there's a 90 degree phase difference. There will be another 90 degree that comes because of multiplying by sine. So this guy is multiplied by cosine. But we will take this and multiply it by sine. Now remember, this is j here minus j. We're writing j on the y-axis to make things simple. But we know there is a 90 degree phase shift. 90 degree from the Hilbert transform. There is another 90 degree from the sine, multiplying by sine. So now if you multiply by sine, it means there is another 90 degree phase difference. So we get a difference of 180 degree and 0. So because remember, the Hilbert transform will give different polarity. One is 90 and one is minus 90. And then if you add, for example, 90 degrees, if you add another minus 90, this becomes minus 100. Let me just write here to show. This is minus 90 and this is plus 90. Adding another minus 90, okay, will make this minus 180 or plus 180. Sorry, minus 180 or 0. So half of the spectrum will be shifted, the other half will remain as is. So if you combine these two together with a plus sign or with a minus sign, it depends on what you do, you can make it upper sideband or lower sideband. So the upper branch give you double sideband, and the lower branch will give you half of the spectrum positive and half is negative. What makes this phase difference is this is going to be make it half of the spectrum positive, half negative, 90 degrees, and this is going to scale by 90. So we get the spectrum of the lower branch. If you like, this is the upper branch, this is the lower branch. Adding them or subtracting them will make it upper sideband or lower sideband, as we see here. I tried to make it simple, but you can pause the video and think about it. Now, here is an exercise. It says a modulated message M of t is given by the following. Okay? Sketch the spectrum of M of t. Sketch the spectrum of the double sideband suppressed carrier signal. From the spectrum, obtain the and suppress the lower sideband, and then write the expression for the upper sideband. We're going to do this using selective filtering. Okay, this is selective filtering. We're also going to do the same design of the single sideband, but we're going to use the phase shifting. We'll apply the expression. And we want to share with you that, of course, we should expect the same answer at the output. So I would suggest that you pause the video here and you try to solve this problem. Take 5-10 minutes, and then if you cannot, or if you can, check your answer with our video here. So let's start. So remember this expression for the message. It's dual tone. We are also given some some trigonometric identity to be used in the solution. So here we need to do is to sketch the spectrum of this message. That should be straightforward. Cosine give you 2 deltas, so this give you 2 deltas at frequency 30, because we have 2 pi times 30 here, and this is going to give you a 20. Remember, the scale factor is half the original amplitude, so we got 2 deltas. This would be straightforward Fourier transform. Now in the second expression, we want to get the double side, the upper side, by multiplying by 2m times cosine 100. So the frequency here is basically 2 pi times 100. So if you want to sketch the spectrum, you're going to shift everything by 100 right and left. The scale of factor 2 will keep all amplitude as is. So we get the spectrum shifted right, shifted left, and there is no scaling now because 2 will cancel with the half. So I got all the frequency components here and shift them by plus 100, minus 100. You got 80 and 70 components, and we have the lower side in the same way. Okay, so the 4 deltas become 8 deltas. So this is, you think of this as double sideband. Now, it says in the question, suppress the lower sideband. How do we know what is the lower sideband and what is the upper sideband? You look at the carrier frequency, it's here. Sorry, it's 100. So whatever below the carrier frequency is called the lower sideband. So I'm suppressing this. This is just the mirror image. So this is going to go out. So what remains is the spectrum. We're done. We have used selective filtering. We have filtered this in and filtered this thing out, and we got our expression as wanted. So now we'll continue with the question. We use selective filtering and we got the expression of interest. Now, if you look at the upper sideband expression, you can write the expression using inverse Fourier transform. So this is basically, in the last expression, we have 2 deltas. These 2 deltas make a cosine at 120 Hertz, and the amplitude should be 2, because what you get in the sketch is half of this, of the amplitude. Similarly, this is another cosine at 130. So this is the upper sideband expression in time, but we got without looking at the equation, we got by selective filtering. Now, if we proceed, if you want to get the same expression, we'll start by finding the Hilbert transform of this signal. The Hilbert transform of a cosine is sine. So, because the Hilbert transform is ideal phase shift by minus pi over 2, so you'd agree with me that the Hilbert transform of the message is just replace cosine with sine. Now, in the next step, we're going to substitute in the general form for the single sideband, upper sideband. And I'm keeping the color here for you to match. The message in blue is substituted here. Cosine multiplied by cosine omega ct, which is 200 by t. And then the green thing is the Hilbert transform multiplied by sine. We use a minus sign here because we want the upper sideband. Okay, what comes next is basic application of cosine times cosine, getting the sum and difference. Okay, and then sine times the sine. Using the identities, we got the following expressions. Okay, and things would simplify, would cancel out. Some of the expressions will cancel out, like these two guys will cancel out in purple, and this is the lower sideband. Also the 80 component will cancel out, and then these two will add up because of the minus here. Minus with minus become positive, and we got the expression here. Now we did this by phase shifting, by applying the equation. Now if you compare this equation with that equation, what do you notice? Of course, you should expect to get the same answer. Now we are done with modulation. Let's start now looking at the demodulation process. Any double sideband suppressed carrier demodulator can also be used for demodulation of single sideband. So remember the demodulation of double sideband, you just multiply by cosine and then use a low pass filter. So to prove this, I would like you to take this expression, which is single sideband, and substitute here. Multiply by cosine and work it out. If we get the message at the output, then mission accomplished. So if you do this, you'll find that if you multiply by cosine the expression, you will get the following cosine times cosine, cosine double the angle, cosine squared, which is 1/2 into 1 plus cosine 4, double the angle. Similarly, sine times cosine give you sine double the angle. So we got the following expression. Okay. If you look at this expression, we have components that are high frequency. So at the output of the low pass filter, the only expression that remains is 1/2 times the message. Why the others will be cancelled out? Because of this low pass filter. And we have shown here that the output is a message, although we have started with the single sideband. So yes, a double sideband suppressed carrier coherent demodulator would work fine for single sideband. If you want to use envelope detection for single sideband, then we need to assume that we add a carrier, and the carrier should be much greater than the message amplitude for non-coherent detection. So if in that case we need to work with single sideband with carrier. Single sideband with carrier, it's the same as a single sideband, but we need to add a carrier here component to make that envelope detection possible. We'll see. We will try to prove this in the coming slides. Sideband. In this slide, we show that we can use envelope detection or detector for single sideband plus carrier. We will start with the expression for single sideband plus carrier. We're using a plus sign here. Okay, and you remember that the plus sign is for the lower sideband. We can always use the minus sign. It would be the same proof, but it's just a matter of sign. So what am I after? I have one cosine, another cosine, and the third sine. If I take this through the envelope detector, an envelope detector, if given one cosine, it will give you the envelope, the amplitude. So I'm not sure what it's going to give me here because I have three terms. My objective is try to combine these into one single cosine. So the first step is straightforward. I have a cosine plus m times cosine, so those together can be combined into one single cosine. Now we have cosine plus sine with the same frequency, but this should be cosine omega ct. Okay, t is not in the subscript. And now we can proceed by trying to write this as envelope times cosine. Remember that cosine and sine of the same angle can be combined together. Remember that if you have a cosine theta plus b sine theta, we can combine them together and get one expression. So we'll try to do this here at this stage, to combine the sine with the cosine. The envelope for this is the amplitude. It's a squared plus b squared under root. So amplitude of cosine, this is the amplitude of the cosine squared plus the amplitude of the sine squared under root, which is raised to the power half. So if we open the bracket, a squared plus b squared, a squared plus 2 times a times m of t. If you open this squared, you'll get 3 terms and 1 term from here, and then I take the a outside, and I got the following expression. The reason I am writing it in this format, I want to see the message relative to a. Okay, so now the envelope, the output, is not really the message, but it has m squared and m Hilbert squared. So let's see, when do you think this can equal to the message? When is this going to be equal to the message? You can see that there is a ratio between mh and a. So we can say that if a is much greater than m of t, and we expect the same will be true for Hilbert transform, then the last two expressions can be ignored. The two expressions in blue, we can ignore them, we can drop them. So then what we get is approximately, now from what comes next, we are approximating. So the envelope would be somehow related to the message, but we still have this issue of square root or raised to the power half. Now we'll use our knowledge of math. Remember, the math says 1 plus x raised to the power n. Under certain condition, when x is relatively small, we get the following series expansion. And although it's raised to power half here, but with the expansion, we can approximate this to 1 plus half times x. So I will do the same here, and this condition should be valid that the message itself should be small. So we can write this. Now this is our expression here. So if you do the same, you get the envelope is approximately equal to 1 plus m of t, divided by a, which is a plus m of t. Okay, but of course, for this to be true, this expression must be very small, which we already requested. So a can be later on, of course, using blocking capacitance, we can drop the a, so we can get the message. So in this slide, we have shown that the condition required to use envelope detection, if you add a carrier, is to make a very large. Remember that this is not something very good, because already a Adding A means wasting power, wasting efficiency. So for envelope detection, AM required A to be greater than M of T. For single sideband, it's not just greater, it should be much greater, which creates some efficiency concern. Now, single sideband is used in telecom channel multiplexing between exchange, and I'm showing you in the next slide how this is used. Okay, now in this slide, just to show you some practical application of single sideband with frequency division multiplexing. For example, in telephony, in some standards, when they send multiple telephone lines, they use the frequency from 60 to 108 kilohertz. This is 48 kilohertz. And then they take the single sideband of every telephone call, they combine 12 of them together to create 12 times 4, which is 48. And then they combine them together. Remember, if you use double sideband, the bandwidth requirement will be much more than this. It will be about 96K. So to avoid this, they use single sideband. And then they use every one group of these, every 12, to create another supergroup out of 5 different groups. So you will see single sideband in telephony in this kind of standard. And of course, you can continue from supergroup to master group. I'm leaving the details here for you to enjoy reading. All right, we can conclude with the following exercise. The exercise says, compare single sideband with QAM. You can pause the video and try to answer. I'm going to go over the answers now, so if you want, you can pause the answer, pause the video, and then start to answer. Comparing single sideband, in the demodulation process, the circuit shown in the side here is the coherent single sideband demodulator. You notice that it is a phase required, it is a coherent detector, but it's less exacting in terms of carrier frequency and phase. So if you compare this with QAM demodulation, QAM requires exact phase because we did the frequency and phase mismatch analysis, and otherwise if you don't have exact phase, the two messages will be combined together, will interfere with each other, you'll get cochranal interference. Now single sideband is good if there is a null at DC, and as shown in the diagram here on the figure. If there is a guard band, then it's possible to implement single sideband to some extent. And remember that without this guard band, then single sideband phase shifter and or filtering are not realizable. Either this technique here is not realizable because you cannot have ideal filter, or even this one is not realizable. I mean, you can approximate, of course, but you cannot have an ideal phase shifter here because it will not be possible to do this for all frequencies. This is a basic comparison between the single sideband and QAM. You can think of other items and share your comments or questions.